Hello class and welcome to section 9.1. Today we're going to go ahead and look at exponential functions. So let's just start by looking at an example of what would represent an exponential function. Sam is working in a biology class with a petri dish of bacteria. He estimates he has a colony of about 25 bacteria. Assuming the entire population of bacteria doubles every hour, find how much bacteria Sam will have after 5 hours. Okay, so this is a representation of an exponential function. And if you didn't know what an exponential function was, you would have just probably figured this problem out by saying, well, at 0 hours, so this is my hours, the number of bacteria. Well, at 0 hours, there's 25 bacteria. 1 hour later, since it doubles, okay, there'd be 50. At 2 hours, it would double again, so we'd be at 100. Okay, at 3 hours, it would be at, well, 200, doubling every time. 4 hours, 200 times 2 would be 400. And at 5 hours, 400 times 2 would give me 800. Okay, so after 5 hours, there would be 800 bacteria. Okay, so we're going to look at how to represent this using an exponential function. But before we go ahead and do that, let's just look at some other functions we have already worked with. Okay, the first one, let's go with, is the linear. Okay, so just remember our linear function. It looks like y equals mx plus b. So remember, it's anything with an x to the first power. Our next function would be our quadratic. Standard form for the quadratic, remember, was y equals ax squared plus bx plus c. So to be quadratic, it has to have an x squared. Our next function is just other polynomials. Okay. So remember this one here, we would count the number of terms to figure out the degree, and the degree is the highest exponent. So there's a turn here, change in direction here, and here. So there's 2. So remember we had 1, so this is really an x to the third function. Here's a change, here's a change, here's a change. So there's 3 changes. 3 plus 1 is 4, so this one is really an x to the fourth. And then here, there's a change here, 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 and here. So that's 4 plus 1 would give me x to the fifth. Okay, so those are our polynomials. Some other things that we have looked at is the square root function. So it is the square root of x, something that has that square root in it. Okay, and just remember the square root of x is something to the 1/2 power. So that square root function started at a point and kind of made this curve. And last chapter we looked at rational functions. So remember, rational functions, typically they have that break. That's where in the denominator it was equal to 0. So remember, this is my vertical asymptote, and that was where x was equal to 3. And it was just by taking that denominator, x minus 3, and set it equal to 0 and solve. So we're at x equals 3. Okay, so that's what our rational function looked like. So today we're going to go ahead and explore what an exponential function looks like. So standard form for an exponential is y equals ab to the x. Okay. One thing that I will say is b is equal to, okay, 1 plus or minus r. And r is the rate at which it is going. Okay, so if it's getting bigger, you're going to add r. If it's getting smaller, you're going to subtract r. And we'll talk about that more in just a minute. Some other properties of exponential functions. Okay, is that the function is continuous and one-to-one. Remember, to be continuous, you keep your pencil down, you don't ever pick it up. So exponential is continuous, and one-to-one means that it, for each input, you only have one output. Okay, if I plug in, 5 and I get out 2, I won't plug in 5 and get out another number. Okay, so one-to-one. There is only one x value for every y value. The domain, which is our x values, is a set of all real numbers. Okay, so you can plug all kinds of values into there. One thing is that the x-axis is an asymptote of the graph. Okay, so if we're looking, here's an example right here down below. This would be an asymptote. Okay, and this is an asymptote, and this is actually the equation where y is equal to 0. It's a horizontal asymptote. So it's the same thing. Okay, so where y is equal to 0. The range is a set of all positive numbers. So a is greater than 0 and all negative numbers. A is less than 0. So basically it covers everything in the range except for 0 because there is an asymptote there. The graph contains the point 0a. Okay, and if you notice, a is in our original function. And what that is this is a is the initial value. Okay, so it's the initial value. It was the number that you started with. Start with. So example, if we go back to our example from the top of the page, well, how many bacteria do we start with? 25. So our bacteria, so our A value for the bacteria problem would be 25. And then one other thing to notice, the y-intercept is A. Well, that makes sense. Okay, so another way to point it out on this graph is right here. This is really the point 0a. So whatever your y-intercept is, that is what A is. And then lastly, the graphs of y equals ab to the x and y equals a times 1 over b to the x are reflections over the y-axis. So if this is y equals ab to the x, okay, there's that one, then 1a times 1 over b to the x as a reflection across the y-axis. Well, here is my y-axis, so to reflect it, it would look like this. Just taking it and flipping it. Okay. So here's our example below. Here's an example of y equals 2 to the x. Okay. As you can see, it's not a fraction. My b value, what's in spot of the b, is not a fraction, so it's increasing and it's going up. If you look here, my b is 1 over 2, so it is a reflection. So as you look from left to right, it's going down. Okay, so it's that reflection across the y-axis there. Once again, notice this is my 0a. Same thing over here. This would be 0a. And if I look at this equation, what number would I really have out in front of here? I would really have 1, so it would really be 1 times 1/2 to the x. So my a value is 1, so here I would have the ordered pair 0, 1. Okay, and if I did the same thing with my last example, this is really y equals 1 times 2 to the x, so my a here is 1, so this is the ordered pair 0, 1. So let's just go ahead and sketch some graphs. All right, so you want to sketch the graph of y equals 3 times 2 to the x, then state the function's domain and range. All right, so if I go ahead and look at this, one thing to maybe take note of is how I did my table. -3 to 2. I would recommend maybe -3 to 3 when you're doing your tables for your homework. But with an exponential, you can always get a good idea if you're starting with, -3 to 3. Okay, so I would recommend doing that. And just like we did with square root functions, you can go ahead and graph this on your calculator and get the values from the table. Okay, so in this case, I'm just going to move it so I can see my function a little better. So I'm going to go to y equals like I have in the past, and I'm going to have 3 parentheses 2 to the, so the little caret, to the x. Okay, there's my function entered in. And then remember, if I want to change my table values, I'm going to go to the table set. So second table set. And I don't want to start with -5, I want to start with -3. And my delta table, that's what it's going to go by. So we're going to go up by 1s. So that's good. Now I'm going to go ahead and get the table. So remember, second table, it's above the graph. Okay, then it gives me the values here. Okay, so I'm going to go ahead and write these values down on here. I'm going to remind you, though, if you don't have a graphing calculator, in order to get the values, all you need to do is 3 times 2 to the, and then make sure you put it in parentheses if you need to. If you don't have a graphing calculator, you most likely do. To the -3rd, and hit enter. Okay, that gives me my first value. Then you could do the same thing to get the next one. So 3 times 2 to the parentheses -2nd. So if you don't have a graphing calculator, that's how you're going to have to get all of the values. If you do, you can go ahead and use the table. So let's go ahead and enter in what we had from our table. So our table had that this was 0.375, and then we had 0.75, then we have 1.5, then we have 3 and 6 and 12. Okay? One thing I would like you guys to notice, what's happening with these numbers every single time that we go up? You should notice that it's getting bigger, and it's getting bigger by multiplying by 2. Notice what my b value is. B is 2, because this is what we call a doubling. Okay, this is a double. It doubles, so it's called a doubling. Okay, so let's go ahead and plot this. So I would have negative 3.375, so just do your best to kind of plot that. Then I would have negative 2.75, negative 1, 1.5, 0.3. One thing I noticed about 0.3 is my a value was 3. And notice how that was my y-intercept. Then I would have 1.6 and 2.12. Obviously, it's not going to fit on my graph, so there it is. My exponential, remember that there is an asymptote here. So it will get really, really close to the x-axis, but it will never actually touch. So just be careful when you draw it not to go through that. Okay. So there is my function. And once again, if you do have a graphing calculator and you want to double check to make sure you did it right, and I highly recommend that you do, is all you need to do is actually go ahead and hit graph. And you should be able to see that it is going up, and it's hitting at 3 on the y-axis. So there is example 1. Okay. Let's go ahead and look at example 2. We're going to sketch this one. One thing I would like you to notice here is what is my a value. Before we even go ahead, my a value is 2. So that means that if I go ahead and plug in 0, I will get out 2. Okay, we can check that when we do it on our calculator. And then just take note, b is 1/2. So what do you guys think will happen if my b is 1/2? Well, when b was 2, it doubled. So if b is 1/2, it's going to be cut in half. So let's just go ahead and graph on our graphing calculator again. So I'm going to go to y equals, clear it out, and then I'm going to type the function 2 parentheses 1/2, so 1 divided by 2, to the x. I can go ahead and check my table set to make sure it's starting at negative 3. Yes, it is, and going by 1, so I go second table, and I get the values this time. Okay, so I'm going to go ahead and write those down on my note sheet. You should do the same. And remember, if you don't have a graphing calculator, you will just need to go ahead and plug them all individually into your calculator. So when I plug in negative 3, we get out 16, then we got 8, then we got 4, and I should check, did I get 2? Yes, I did. Then I would get 1, then I would get 0.5, so 0.5. So notice every time it was cut in half, so this is halving, okay, or halves. So I'm going to go ahead and sketch it. So I'd have negative 3, 16. That is not going to fit on my graph, so I don't need to put it on there. Negative 2, 8. Negative 1, 4. 0, 2, 1, 1, and 2.5. Once again, remember that there is an asymptote here, so I will never touch that, so do not make it touch that. And do your best to connect them. Mine kind of touched. Maybe I should undo that one and redo it again. Gonna get really, really close, but not actually touch. All right, and there is example 2. So, some things that we have talked about is growth and decay. Okay, I would like you to notice example 1. As we look from left to right, it is getting bigger, so it is growing. If you look at example 2, as you look from left to right, it is getting smaller or decaying. Okay, so exponential growth. Well, it's going to be B. One thing I would say is 1 plus R, which is the rate at which it's growing at. Okay, and with exponential growth, your A value has to be greater than 0. It's going to be positive. And B, well, if it's always 1 plus R, is also going to be greater than 0. Sorry, greater than 1. Greater than 1. B will always be greater than 1. Okay. With exponential decay, so as you look from left to right, if it is going down, okay, okay, if your graph looks like that, then your B will equal 1 minus your rate, okay? And your A will be greater than 0, so your A will still be positive, but one thing to do decay is it will be from 0 to 1, your B value will be. Okay, it won't be greater than 1, it won't be less than 0, so B will be in between 0 and 1. Some things that we need to talk about. What will the value of this do? Okay, well, would this be exponential growth or decay? If you buy a car and you keep it over time, will it grow or decay? The value will decay. Gold. What will happen to the value of gold? Typically it grows, so this is growth. When you purchase a house, typically the value of a house will grow. Sure, there are some instances where it doesn't, but over the long run, it will. The value of these two things will grow and increase. And then lastly, technology. Think about your phone. Whatever phone you have now, will it still be as valuable as it was when you bought it 2 years from now? No, it will not. So this is decay. So technology is decay. All right. So here's some functions that we need to decide if it's growth or decay. So if I go ahead and look at example A, I would see that my A value is 1, because 1 times that will give me my A, and my B value is 1/5. All right, so I would look back at my notes if I needed to, just a little bit above, and I would say, well, B, is it greater than 1 or is it in between 0 and 1? Well, 1/5 is in between, so that would make it a decay. Okay. Here, my B value is, remember it's always the one with the X, is 1.2, and my A is 7. Okay, but we're concerned about my B value right now. My B is 1.2, so that's greater than 1, so that would make this one a growth. All right, so now we're going to actually do some problems. Okay, suppose you buy a car for $15,000 and its value decreases at a rate of about 8% per year. Okay, so we need to write an exponential function for the value of the car after X years. Well, we know that y is equal to ab to the x. That's our exponential. This decreases, so b will equal 1 minus my rate. Okay, well, my rate is 8%. We don't leave it as a percent, we put it as a decimal. So remember, we move the decimal over 2, so 8% is 0.08. So my b is equal to 1 minus 0.08. Okay, if you do that on your calculator, you get that it is 0.92. Okay, so now I can write my equation. Y is equal to, my A is your initial amount or the starting value. Well, the starting value of my car was 15,000. 15,000 times my B, which is 0.92, to the X. There is my equation after X years. That will be the value of the car. Now it says, what will the value of the car be after 4 years? Well, all you need to do is go ahead and it says 4 years. Well, that's X years, so I plug in 4 for X. So on your calculator, you would go ahead and you would go to the main screen and you would do 15,000 times 0.92 to the 4th and hit enter. And you'll see what it is. Notice there's 4 decimal places on this, but we're talking about the value, and the value's in money. So make sure when you do value, you always round to 2 decimal places. So this would be $10,745.89. That will be the value of the car after 4 years. So $10,745.89. That's the value of the car. Okay. Let's go ahead and look at example 4. Example 4, before we go ahead and move on, if you have any questions, I would go ahead and write them down. If you need to take a break, pause the video, go ahead and do that. Stopping at 4 would be a good place to stop. So let's go ahead. Suppose you have an experiment with 45 bacteria that double every hour. Well, we're starting with 45 bacteria, so that's your initial amount or your A. So that means A is 45, and it doubles every hour. Well, what happened to the problem earlier when we had the numbers doubling? That was when my B was equal to 2. So write an exponential function for the amount of bacteria after X hours. Well, Y is equal to my A, 45, times 2 to the X. There is my equation. And part B, how many bacteria will you have after 4 hours? All you're going to do is plug in 2 for X. Sorry, not 2. You're going to plug in 4 for X. Type that in on your calculator like we did on the previous problem, and you will get that it is 720 bacteria. I would encourage you to check to make sure you can type it in on your calculator and get the same answer as me. All right, example 5. In 2000, the population of Phoenix was 1,321,045, and it increased to 1,331,291 in 2004. Okay, it says write an exponential function that could be used to model the population Y of Phoenix. Write the function in terms of X, the number of years since 2000. Okay, this is key that it says number of years since 2000. So what it's really saying is my initial or my starting out value is 1,321,045. So this is really my A value because it started in 2000. Okay, that's our starting point. And it increased to, well, they're telling me an ordered pair here. How many years after 2000 is 2004? Well, it's 4 years. And we had this many people. So really what I have is an ordered pair here. And this represents X, this is Y, and here's my A. So what do I not have for my equation? Y equals AB to the X. I do not have B. So we need to go ahead and find B. So I'm going to go ahead and plug in everything that I know. I know what Y is. It's 1,331,291 is equal to my A, 1,321,045. Then my B, I don't know what B is, and I know what X is. X is 4. So I need to solve this equation. So what I would need to do is divide both sides, okay, because I'm solving for B, by 1,321,045. Okay, these will cancel. On my left-hand side, okay, if you type it in on your calculator, you will get 1.0019. I'm just going to give you the whole screen that the whole value on my screen on my calculator when I did this. Equals B to the 4th. Okay, so I'm just going to pull up the calculator right now and do that. I'm going to divide these two values to show that I will get this number. So I'm going to clear this off, and I have 1,331,291 divided by 1,321,045. Okay, and that's the value that I get. Okay, now I'm going to use this number to actually figure out what B is. How would I figure out what B is? I have B to the 4th. How do I get rid of that 4? Well, in order to get rid of that 4, I would have to take the 4th root on both sides. Okay, so my 4th root and my 4 will cancel out. And if I go on to my calculator, B will be approximately, okay, and when you do this, I want you to use the most exact value on your calculator. So you're going to do the 4th root. So if you have a calculator like this, you're going to go 4 math, and then down to number 5. See how it has the X root? There it has the 4th root. And you're going to arrow up, or you're going to retype it in. Okay, so now I have the 4th root of the number that I have from before. And here is my B value. B is 1.0019333381. Okay, we're going to write down 4 decimal places, so it's going to be 0.0019. Okay, so B is approximately 1.0019. Okay, so it says write the equation. So my equation, here's my B and I use my a from before to write the equation. So for part A, my equation is 1,321,045 times my b to the x. So there's my answer for part A. For part B now, it says, suppose the population of Phoenix continues to increase at the same rate. Estimate the population in 2015. Now, you cannot just go ahead and enter in 2015. Okay, you have to remember x is the number of years since 2000. So you would do 2015 minus 2000 to figure out how many years it is. This one's nice and easy because you can count. That one's going to be 15 years. And then into my equation, I would plug 15 for x. And I'm going to show you how to do this on your calculator because I want the most accurate answer possible. So we're actually going to use the entire b value from before. Okay, so we are going to do, it was 1,321,045. Okay, times our b value, which was 1.0019. We're going to go up arrow to get that and hit enter. To the, and we said how many years later? 15th. 15 years later, enter. There is my population. One thing you need to take note of is, can you have 0.11 of a person? No, you cannot. So I would say that the estimated population will be 1,359,879 people. Okay. Let's go ahead and write that down. And there is my answer for number 5, part B. All right, then we're going to move on to example 6. If you had any questions on example 5, please go ahead and write them down. Example 6, it says solve the exponential equation. So if you look at part A, notice how the bases of both of these are 3. So if my bases are exactly the same, I can just go ahead and take my exponents and set them equal to each other and solve. So really I have 2n plus 1 is equal to 4. I would subtract 1 from both sides, so I have 2n is equal to 3 and divide by 2. So n is equal to 3 over 2. Or 1.5, whichever way you'd prefer to write it. Okay. If I look at example B, though, my bases are not exactly the same. So this is kind of a problem. But I can think about, well, this one has a base 2. Could I rewrite 8 as base 2? Well, I know 2 to the second is 4, but 2 to the third is 8. So I'm going to use the fact that 2 to the third is equal to 8. So I will have my left-hand side. So I have 2 to the second to the 2x is equal to, now in place of 8, I'm going to write 2 to the third to the x minus 1. Now my bases are the same. Okay. And remember, when I have a power to a power, I multiply those. So 2 times 2x will give me 4x is equal to 3 times x minus 1. I'm just going to write it 3 times x minus 1. Okay. I would distribute that 3 on my right-hand side. That's what I did there. And now I will go ahead and subtract 3x from both sides. 4x minus 3x gives me x is equal to negative 3. So there is my solution. And we have one more example, part C. This one has a fraction involved. Okay, so let's just first of all think about, well, 1 over 64. Okay. This one is base 4. Is there something to the 4 to some power? Is there 4 to some power that will give me 64? Well, if I think about it, 4 to the third is equal to 64. So I'm going to write that down over here. So I'm going to rewrite my equation. I have 4 2 to the n minus 1 is equal to 1 over 4 to the third. Now we just have to remember our rules of exponents. If it's in the denominator and I move it to the numerator, the sign of the exponent changes. So it's positive, but if I put in the numerator, it's negative. So I have 4 2n minus 1 is equal to 4 to the negative third. Now, if you notice, both of my bases are 4, so I can just take 2n minus 1 and set it equal to 3 to solve. So take that over here. So I would have 2n minus 1 is equal to negative 3. I would add 1 to both sides. And what I have is 2n is equal to negative 2. If I divide by 2 on both sides, I have that n is equal to negative 1. And there is my solution. Okay. That will be the end of the section 9.1 notes video. If you have any questions, please write them down. Please ask me tomorrow in class. Otherwise, have a great night, and I will see you then.